Okay, this section, we're going to look at a different way to find the volume of a curve that is rotated around either the x or the y axis. But first I want to show you why we need a different way before we get into it. So let's suppose I have a curve that is, and this is number 10 in 6.4, so you can see where they're coming from the textbook. So my curve is the function, well, I'll write it this way. First, 1 over 1 plus x squared, which of course is the same as 1 plus x squared to the negative 1 power. Y equals 0, x equals 0, x equals 2, but I'm going to rotate it about the y-axis. So before we get started, we need to see what this thing looks like. So let's draw a quick graph. And again, this curve goes something like this. And here is your x equals 2. So this is my curve, y equals 1 over 1 plus x squared. And you can pop that into Desmos and confirm that's what it looks like. And you might think, well, that's fine. I want to rotate around the y-axis, around the y-axis here. So I'm just going to draw my circles like we did before. Well, you're going to run into some problems right away. First of all, look at this function. You have to change the function because we're going around the y-axis to do it the way we described in the last function, in the last video, which would be with all the circles, right? I would have to get this function to look like, I'm going to just start moving it around, 1 over y. I just multiply both sides by y and then divide it by 1 plus x squared. So x squared is going to be equal to 1 over y minus 1. What I'm doing here in blue, I don't suggest you write down because you're just going to run into a problem, and hopefully you'll see that problem pretty quickly. We would have to see what the function is when x is at 0. That's pretty easy. It would go from 0 to 1, right? This would be 1 when x is 0. But we run into another problem. Well, we run into a few problems here, and hopefully you can see it. We can only do those circles up to this point. Do you see that? So if we wanted to integrate pi 1 over y minus 1 squared dy, we would then need to integrate, well, you got to figure out what this value is. So when x is 2, we have 1 over 1 plus 4, we have 1/5. We would then have to integrate from, sorry, this isn't 0. Apologize for that. This is actually 1/5. From 0 to 1/5 of 2. Oh, that part, the easy part, right? Of 2 of, not 2, of pi times 2 squared. Okay, so yeah, that second integral's fine. I want you to just ponder on that first integral for a second. If we try to use u sub, derivative of u, if you recall, when you have y to the negative 1, du dy would be y to the negative, so be y negative 2 over y to the squared. Anyway, negative 1 over y squared minus 0. Well, you don't have a 1 over y squared in this function. You can't integrate that with the techniques you know at this point. So there's your second issue. First issue is, yes, you have to separate it into 2, and you've got to recognize you need to separate it into 2 integrals. But the second one is to realize you can't even do it because you don't have the techniques to do that integration. So, not going to work. Fortunately, there is another way to think about this. And this one is a little bit harder to see at first. Instead of doing circles, and which then form a disk, we can do our shell. So the shells end up being, think of taking it this way and looping it around. Right? And to help us out, I kind of showing you these figures because I think it would be a little bit easier to see. So look at this first one here. These shells kind of progress as we add more. And you end up with a figure that looks something like this. So you can see the individual shells. What these shells are almost like hollowed out cylinders. Each individual shell, right, is a hollow cylinder. But notice that each shell is actually parallel or perpendicular to our x-axis. And the infinite number of shells that are occurring against, again, standing up against perpendicular to the x-axis. So even though we are revolving around the y, when you do the shell method, you differentiate to the opposite axes. And that is one of the biggest difference between your shell and your disc and washer. With your disc and washer, if you're rotating around y, you differentiate with respect to y. But with shell, you have to do the opposite. So let's talk about these cylinders. The height of each of these cylinders then, well, that is dependent upon your f of x value. And it's going to change dependent upon f of x. We are no longer looking for an area, that bottom piece of a circle, because these shells, as you can see when you look into them, are hollow. So if you're not looking at the entirety of the circle, just the outside of the circle, now we're talking about a circumference as opposed to an area. And your circumference of your circle is 2 pi r. But what is r? For each of these shells, if this is your f of x, that is your x value. So your circumference becomes 2 pi x. And if you go through the process of summing them all together, your volume becomes the limit as n goes to infinity of the summation of these cylindrical shells. So what does that look like? The volume in this case, a to b. We have 2 pi x times f of x. There's no squaring it because there's no radius. dx. This is a shell that revolves about the y-axis, but this particular one, just to clarify, has the x-axis as a boundary. So we don't have to subtract out another function. The more general would be volume equals a to b 2 pi x That's if you have a secondary function where this represents the shell height. Keep in mind, in a lot of problems, there won't be a g of x if you were just subtracting right to the x-axis, which is just 0. And this piece is your shell circumference. Okay? And this is about y-axis. We've done enough of these now that you can, I would assume, be able to change that to a shell about the x-axis. If we want to go and revolve it around the x-axis, remember, we're actually differentiating with respect to y. So we'll use our C and D, and I'll use my P and Q. So now we have 2 pi y, just y, P of y minus Q of y dy. Big difference. You've got to think about it. You can memorize them, but if you just think about them and can visualize, let me go back up for a minute. You can visualize what they are. You can kind of remember, oh, okay, shell, that's a circumference, so it's 2 pi x times f of x, 2 pi y times p of y. And of course, if you're not bounded by an axis, you're bounded by another curve, you got to do your f of x minus g of x, or your p of y minus q of y. Biggest thing to remember is you need to differentiate with respect to the other axis. So, let's go back to our original problem, which was 1 over 1 plus x squared. And we'll use this formula to set it up. So y equaled 1 over 1 plus x squared. And then we had y is 0. And x is between 0 and 2. And we were revolving about the y-axis. So we're going to go a to b on the x, so that's 0 to 2. We're going to go 2 pi x, that's just our circumference, times my function, 1 plus x squared dx. Hopefully you can remember, you use sub and almost see right away that, well, now, if I let u equal 1 plus x squared, du dx is 2x there's your 2, there's your x, there's your dx. And this fits really nicely into a u sub problem. I can pull out my y. So again, and if we want to really do a full u sub on this one, you can choose to, you don't have to, you can change your limits. What that means is you come over here to 1 plus x squared. Well, when x is 0, you can see when x is 0, this becomes a 1, and the 0 goes to 1. When x is 2, that becomes a 5. So really going from 1 to 5. Our 2x dx becomes du, so 2x dx becomes du. The pi can go out front, and we're left with 1 over u du from 1 to 5. One didn't finish. And you can quickly integrate that. And you can put your function back. This was kind of a shortcut to u sub, where if you change the limit, you can keep it as a u. Remember, you have to do one or the other. If you don't change the limits and you keep the limits from 0 to 2, you have to substitute your 1 plus x squared in before you evaluate. But if you choose to change the limits, you don't have to substitute your 1 plus x squared in. Keep that in mind. So this is just going to give us now pi, that's ln of u from 1 to 5 minus pi ln 1, and e to what power equals 1, that's 0, that goes to 0, so your answer's pi ln 5. And that is your area. Now, when you do the lab on this, there's going to be a lot of problems where I'm not going to ask you to finish integrating it. I'm simply going to ask for the setup, in which case you can stop here. And you don't have to do any other way. Again, not that this couldn't be done the other way, using circles. You would just have a very difficult time integrating it. But if I ask for a setup, you can certainly set it up using the disk method, and you can set it up using the shell method. So this is the shell, and we had set it up previously using the disk. The problem we ran into is we couldn't integrate it using the disk method. But again, on the lab that I give you for this, I am really only looking for you to set things up. You're not solving all these integrals. Okay, this next one I'm going to do is probably one of the more harder problems, but I think it'll give you a good feeling for these types of problems, and, well, we'll make some of the others seem a little bit easier, right? So this one I'm going to take also from the textbook. It's going to be number 16. And for this one, we have x equaling 4 over y plus y cubed. Then we have x equaling 1 over square root of 3 to x. Oh, and y equals 1. There we go. I'm going to rotate about the x axis. So let's just draw it first. So my function 4 over y plus 3 is going to kind of look something like this. Here I have x equaling 1 over radical 3. And if I go ahead and plug that in, when x is 1 over radical 3, I get y equaling 1. And well, not when I plug it in, but when I put these in here. Sorry about that. I don't get 1. When I plug in 1 over radical 3, I actually get radical 3 up here. And then when it's 1, it comes out to 2. Let me fix my curve a little bit, trying to get this as accurate as possible. So I want my triangle to be here. Yeah. And the curve kind of goes like this. There we go. That's a better representation of what I was attempting to do. Yeah, that's better. Because when y is 1, when you plug it in, you clearly get x being 2. What I want is this region right here. Okay. We're going to go about the x-axis. So we're going to rotate around our x-axis. So our shell's going to go this way, right? Or at least the piece of our shell, the piece of our cylinder, and then it's going to come down here and finish off down here. Now the reason it would be very difficult to convert this y and solve for y to get an x for this particular function. So we're going to keep it as it is. We're going to use our shell method and revolve it around the x-axis. So using that method, according to the formula, so we are going to go, since we're revolving around the x, we're actually integrating with respect to y. So we're going to go from 1 to radical 3 in our integral. Okay, and then it's 2 the circumference of these, the base of our cylinder that is formed is going to be 2 pi y. And the height of our cylinder is actually found by subtracting these 2 curves. And these 2 curves are 4 over y plus y cubed minus just 1 over radical 3. It's the curve x equals 1 over radical 3 dy. So again, on the lab, I'm just looking for a setup, in which case you'd be done. You wouldn't have to go through it. I think this is good practice. It brings in a function we haven't used yet. Could have maybe used on that first problem, but we'd have had to square it and it would get a little more complicated. But we're going to use it here, and you'll see it in a minute. So I'm going to kind of play around with this function a little bit. I'm going to distribute my y through to make it a little bit easier. I'll take out 2 pi, 1 radical 3. When I distribute y through to the first part of the function, it's going to, you can pull out a y at the bottom, cancel it, so you end up with 4 over 1 plus y squared. And when I multiply the y here, it's just y over radical 3 dy. All right, so, all right, you might be looking at this first function like, well, if I try to do u sub, I get u equals 1 plus y squared. Again, I think that first problem we were working on, it was square. Then that was also squared, made it a little more difficult. This one, yeah, do you remember what the integral of 1 over 1 plus x squared is, for example? And this is where you have to go to your trig inverse functions. You probably only touched upon them briefly in Calc 1, but I know I had told my class one of the ones, especially if you're going on to Calc 2, is to memorize them, especially the sine and the tangent one. This one happens to be tangent. So when we integrate, the 4 just stays 4, all right? And we end up with tan inverse of y. That's what the integral of 1 over 1 plus y squared is. So that one's going to come up from time to time, so you're going to want to memorize that one. And then subtract. That's your first one, subtract. We need to integrate y over square root of 3. So y becomes y squared. You got to divide by that. So you have 2 square root of 3. And this all goes from 1 to radical 3. So at this point, you're just working with your trig functions again. We'll go through it kind of quickly here. Okay, so I'm plugging in radical 3. Tan inverse of radical 3. You can use your calculator. Of course, you're asking yourself, hey, what angle gives me radical 3 or radical 3 over 1? That happens to be pi over 3, or a 60-degree angle. Okay, minus, now plug in radical 3. If you square radical 3, you just get 3 over 2 radical 3. Minus, now I'm going to plug 1 into everything. Okay, what angle gives, well, that's an easy one, because the only way when you do opposite over adjacent, you're going to get a 1 is when those two things are equal to each other, and that's a 45-degree angle, so that's going to be pi over 4. And plug in 1. So again, the lab, I'm not going to make you go through all this. The homework, you're going to have to go through this. On a test, yes, you're going to have to simplify unless I specifically state you do not. It may not be this crazy because this will take a little bit of time to kind of go through it, but you want to make sure you got it right. So we have 4 pi over 3 minus, that becomes pi over 4 plus, right? We'll just work it out real quick. 4 pi over 3. No, that just becomes pi. See? So easy to make a mistake. 4 pi over 4 becomes just pi. Sorry about that. Some of you are probably sitting there thinking, where is she getting pi over 4 from? That's just pi. All right, so 4 pi over 3 minus pi, which you can write as 3 pi over 3, is just pi over 3. And negative 3, 1 becomes 2, becomes just minus pi 1 over, yep. All right, so you have negative 3, 2 pi over 3, plus 1, 2 pi over 3 becomes negative 2 over 2 radical 3. Sorry, I keep saying pi 3. And that just becomes 1 minus radical 3. You know, I don't know how far Math Lab's going to make you want to go. If you don't like the look of this, you can certainly clean it up a little. We usually don't like to write 1 over 3. That's radical 3 over 3, right? Multiply by radical 3 over radical 3. You can pull out 1 over 3 and have pi minus radical 3. However, you want to write the answer. So again, that one's a little bit more complicated, but hopefully, you know, the other ones are easier. How did we know this one ended up being, you have this, you know, we're revolving around the x-axis, but we've got this empty space. So as soon as you have the empty space, we have the empty space here. Sorry, we're differentiating with respect to x. We don't have the empty space there because we're differentiating with respect to x. That's what you want to look at with respect to y. Sorry. We're differentiating with respect to y. We have that empty space there. So when we get the height, and that's what you want to look at, the height of your shells. When you get your height of your shells, it's going to be the curve minus the, so apparently I've made too many videos today, so I'm going to call it a day because I keep saying the wrong thing. Again, differentiating with respect to y, have an empty space between where our open cylinders are and our y-axis, you're going to have to subtract to get that height. When the height goes all the way down to the axis, that's when you don't have to subtract everything because you're up against the y-axis. All right, so hopefully I didn't confuse you with too much there, and we'll call it a day, and that is 6.4 volumes by Shell.